Welcome to PPL Expert. My name is Tom and I'll be presenting the Meteorology course. This course is designed to give you an in-depth understanding on the theory required to pass the CAA theory exam for this particular topic. Despite this, own self-study, commitment and discipline will be required. The course is displayed in the form of a slideshow, which I'll be talking through. Please feel free to pause the recording at any point to either take a break or write down any notes. So the overview of what we'll be looking at the atmosphere, something called ISA, the International Standard Atmosphere, pressure, altimetry, visibility, the wind in different air masses, icing, cloud, thunderstorms, and then weather forecasts and reporting. So we'll look at the fundamentals of weather and then why it's applicable to us as pilots. So why do we need to study meteorology? Why is it important to us as pilots? So firstly, we need to understand the physical processes of the atmosphere, so how the atmosphere works and how that can relate to weather. Secondly, we need to understand the hazards associated with the weather, identify weather information and interpret it from different weather stations, be able to understand forecasts for a flight, and then also devise solutions to problems that could occur. So if we've got a solution with weather, understanding the process of the weather and how weather systems work may influence our decision of how we're going to solve it. So the first topic we're going to look at is the atmosphere. Now the atmosphere is divided into 4 separate regions. So we're going to be looking at those and also what is most applicable to us. So we have the atmosphere itself, and that's comprised of the thermosphere, the mesosphere, the stratosphere, and the troposphere. And the troposphere is where all of our flying will happen, and it's where the airliners will be flying as well. And then the troposphere is that lower region closest to the ground. And most of the weather occurs within this region because of a couple of factors. Firstly, temperature drops with altitude. So as altitude increases, the temperature will drop. Density drops, so the density of a parcel of air, so how many air molecules per parcel of air will decrease with an altitude increase. And also pressure will also drop with altitude as well. Within this region, the troposphere, the vertical movement of the air is the greatest, so warm air will rise up and cool air will want to sink. And this region also contains almost all of the water vapor, which is why it creates that weather. So the Earth spins on an axis, and the axis goes through the North Pole and the South Pole, and it carries the atmosphere with it. So as the Earth spins, it carries the air above it around with it as well. And that's why the atmosphere extends further above the equator, so it's carrying the air mass as it turns. The atmosphere is thickest where the surface temperature is greater. So around the equator, the atmosphere is thicker compared to the poles where the atmosphere is slightly thinner. Okay, so we have a greater vertical extent around the equator than compared to the poles. So we looked at the 4 different layers, and the one that all the weather happens in generally is the troposphere, and then above that we've got the stratosphere. Now, the boundary between the two layers is known as the tropopause, and it occurs at different altitudes depending on the latitude of so how close or far away we are from the equator or the poles. So around the poles, this tropopause is at around 20,000 feet, whereas at the equator, it can be all the way up to 60,000 feet. Now, we said before that the troposphere contains most of the weather because the density and the pressure will change, will reduce, but also the temperature will as well. However, when it gets to the tropopause, at this point the temperature will remain constant. So instead of decreasing, it will stay the same, and it's normally at a standard figure of minus 57 degrees, and it will stay constant for quite a few hundred thousands of feet, at which point, as it goes further in the atmosphere, that temperature will start to increase again. So looking at the atmosphere and the composition of the air, and the composition of the air through the atmosphere remains the same. So in any amount of air, for instance a cubic meter, 78% of that air will be nitrogen, 21% will be oxygen, and then 1% will just be considered other gases. Now, that percentage will always remain the same, and as we go up in altitude, the density will change, so the amount of air molecules per amount of air will get less. However, the composition of the air will still remain the same. So there'll still be the 78% of nitrogen, still be the 21% of oxygen, and 1% of other gases. That will not change. It'll just be how dense an area of air is. So the sun radiates electromagnetic energy, and that's how we experience heat and also light. And a large percentage of solar radiation penetrates the Earth's atmosphere and then is absorbed by the Earth, and that's what's going to cause the temperature of the Earth to rise. As this radiation hits the Earth, it will heat the Earth and then also heat the ground around it. As this ground heats up, it will also heat the air just above it, and that will cause air to rise, and this is known as convection. Okay, convection is where air is heated from below, and then the air is rising up as it goes up into the atmosphere. Now, depending on geographically where you are in the world, this solar radiation strikes at different angles. So if we're over tropical regions, it's going to strike directly overhead. But as we know, the Earth is on a tilt. So that means that because the Earth is tilted, this concentration, it's the solar radiation hits the Earth at an angle, so it's a more concentrated area of where this solar radiation is emitted, and therefore smaller. So even at polar regions, this solar radiation is going to be almost nothing. So near the tropical areas, it's the greatest amount of concentration. As we get further away from these tropical areas towards the poles, the area gets smaller, and therefore the least concentration as well. So as you probably already know, there's a lot of planets in the solar system, but our planet Earth, it rotates around the sun. And the Earth itself orbits the sun once every year, or every 365 days. Now, because the Earth is tilted, and that tilt is around 23.5 degrees, this is what gives us the different seasons. So depending on where the Earth is within that cycle, because of the tilt, gives us the summer, spring, autumn, and winter. And it's a combination of how close we are to the sun and also the tilt of the Earth at that time. And the Earth is closest to the sun on the 3rd of January, and this is known as perihelion. And the Earth is the furthest away from the sun on the 4th of June, and this is called aphelion. So it's important to realise that the distance between the Earth and the Sun is not important to the amount of heat radiation we get. So as you can see, we're closest to the Sun on the 3rd of January, but in the Northern Hemisphere, that's our winter. What's more important is the angle at which the Earth is tilted at. That makes the difference for the seasons, not how far away or how close the Earth is to the Sun. So now we're going to look at the movement of different airs. Okay, and as you probably expect, towards the equator, also known as the tropics, there's a lot more heating of the air as it's got more area of solar radiation. As that air heats up, it's going to cause more movement. And generally what happens when air heats up, it wants to rise, it wants to ascend within the atmosphere. And it's going to expand as well and therefore become less dense. So this movement of the air is called general circulation, and it causes different cells around the globe. Okay, so ascending and descending air at different latitudes create the general circulation and these cells. So from the equator up into the subtropical high and low latitudes, we have the Hadley cell. Between the latitudes and the polar easterlies, we have the Ferrel cell, and between the polar easterlies and the North Pole, we have the polar cell. So this ascending and descending air is creating this circulation of air which affects the weather around these regions. So here's an example of the equator being 0 degrees, and then you've got 30 degrees north and south. Now, around the equator, it's a lot of hot air. That hot air wants to rise up, and this is going to create this ascending air, and it will converge at the bottom, rise up, and cause something called divergence at the top as that air wants to diverge out. So around the 0 degrees, the equator, it's going to create an area of low pressure. Okay, and we'll look later on about what kind of weather is associated with that low pressure. As that air rises up around the equator, it's going to cool, and eventually it's going to cool to a point where it's around the temperature of the atmosphere around it. Then what will happen is once it's cooled, it will start to descend back down again. And as it descends, it's going to create an area of high pressure. So around 30 degrees north and south, you get a band of a lot of high pressure weather and areas. And again, we'll look at the sort of weather that's associated around those regions. And you'll see that geographical locations have very consistent weather based on these, because of these Hadley cell, or the Hadley cell, this converging and divergence air, which creates a uniform sort of weather system. So at the equatorial trough, or at the equator, the air will heat up, it will start to rise, and that is known as convection. And we know it was going to create an area of low pressure as the air starts to rise. And at the top of the equatorial trough, the air will cool, spread out, and that is known as divergence. Okay, so convergence is air coming together, and divergence is air masses moving apart. That's ascending. If we look at descending, that sort of right picture, you see convergence, that air coming in together higher up, descending